Tony, K1KP, and I put on this talk at the forums at Nearfest, and Dennis, not to miss an opportunity, buttonholed me and said, "Hey, will you do it for the club?" And I said, "Well, it's really pretty basic, and I'm pretty convinced that there's about 5 or 6 guys in the audience who are going to be correcting me. So I would ask anybody to whom this is old hat to be merciful. But other than that, this is going to be a very basic, very introductory level talk on antenna modeling. And it really came about because about 3 months ago, our intrepid AV guy here asked me if I could teach him how to do some antenna modeling because he wanted to try to do some modeling on the 3 stack of tri-banders at K1VR. And that's sort of like jumping in the ocean before you know how to swim. But I said, sure, I'll be happy to teach him what I know. And unfortunately, I don't think his high school schedule agreed with being there on Friday at Nearfest. But anyway, here's what I got. I've got a slide deck, and I'm going to go over a bunch of generalized terms and stuff. And then I'll actually jump in and do some modeling. So I'm going to get rid of all of that stuff. No, this is not EasyNet. I'll talk about EasyNet a little bit, but this is basically the program I use is 4NEC2. So, introduction to antenna modeling. Anyway, we'll talk about why you might want to model an antenna. What does modeling tell you? Some of the important parameters, choices of programs, how to input your antenna dimensions, how to run the simulation, how to do something called optimization. I'll give a few examples and I'll take questions. So probably it's best if you just go ahead and speak up and ask questions as we go along. So I have a few slides and then we'll just get into the real nitty-gritty of running 4NEC2. So why would you want to model an antenna? Well, you might want to figure out a design that will work. You might want to figure out what will work in your particular location. You might have some unique constraints in your location. You might want to find out why your antenna doesn't work in your location. Or you might want to design your own antenna, a fancy mousetrap ZEP or something. So those are some of the reasons why you might want to model an antenna. So what does modeling tell you? Well, now we're going to get into some of the terms that we use, and I'm going to go over these terms because they can be a little bit tricky. So basically, modeling can tell you the gain of an antenna. It can tell you the efficiency of an antenna, and I'll explain what these terms mean. It can tell you what the input impedance is or what the SWR is likely to be if you feed it with a certain kind of feed line. It can tell you stuff like vertical takeoff angle, which can be important if you're interested in working DX. It can tell you about interactions with other nearby antennas or structures, and that can be important. I know in my case, I've got basically 2 towers. One is an 80-footer that has gain antennas for 80 through 10, and then I have another tower which is a 50-footer that has a 20 through 10 quad on it. And the whole idea of trying to get a 160-meter antenna in there somewhere is a challenge, and a lot of it has to do with interaction with the towers that are already there. And modeling can also tell you the effect of your particular ground, whatever that is, and also the effect of radials. So we'll start talking about the important parameters. We'll talk about gain and directivity. And quite often when somebody is trying to explain antennas and they talk about gain, they give you the example of the squished balloon. And so basically the concept is if you have something that radiates energy equally in all directions, it's like a round balloon. But if you can somehow squeeze that balloon and take some of the energy that was going one way and send it in a more desired direction, you essentially increase your gain and you increase your directivity. And so there's the squished balloon example, but I like the flashlight example, which is better. So if we take a flashlight here, and we basically got a bulb and a bunch of batteries, and so this one here is emitting light in about half of a balloon. Obviously, the light is shaded by the flashlight down below, but and it doesn't matter which direction I hold it, so it's a pretty good omnidirectional antenna. But if we put a reflector behind it and force all of the energy to go in the same direction, then it's much brighter, right? So this is kind of the idea of gain and directivity. So we've increased the amount of signal going in the desired direction, which is however I point my flashlight, and we've also reduced the angle over which it's being distributed. So gain typically means how strong is one thing as compared to something else. So there's the thing you're trying to describe, and then there's a reference. And unfortunately, in the world of antennas, there are at least 3 different references, and we'll get into those. And those are used very carefully by antenna manufacturers to create the maximum confusion. It's sort of like a cell phone plan, or buying health insurance. It's designed to maximally confuse in order that you might make a mistake and pay more than you need to. We'll talk about efficiency. Now, efficiency on an antenna is how much energy actually came out of it in the form of useful RF as compared to how much energy you actually put into it in the terms of your 1500 watt amplifier. And so obviously we want an antenna that's going to convert all of our RF electrical power into an electromagnetic wave that's going to be received by someone at a distance. We'll talk about front to back. Front to back is basically the ratio of energy that's going in the desired direction versus the energy that's going in the opposite direction. We'll talk about takeoff angle, which is basically when you put an antenna over ground, all of a sudden, like the flashlight, the energy can't go below ground, so it has to go someplace else, and we'll find that that energy that was going to go through the ground actually combines with the energy that's coming directly from the antenna, and that creates an effect which is essentially a maximum at some vertical takeoff angle, and we'll see how that can be seen by modeling. We'll talk about other interesting parameters that modeling can tell you, like input impedance, resonance, bandwidth, your ability to deliver power from the radio to the antenna, and those numbers can be independent of gain and directivity. So I'll give you a couple of examples. I've been trying for years to come up with a decent 160 meter antenna. I came up with one that would fit on my property. Now I have one rule, one of many rules, which is I don't do radials. So any antenna I have has to be able to work without radials. And for 160, because of the amount of length involved and because of the fact that if you have a low antenna that's horizontally polarized, it's not going to work very well on 160. So the best antennas on 160, given a height restriction of something moderate like 80 feet, are going to be vertical antennas. Now, vertical antennas typically want ground radials to work well unless you can make them actually a balanced antenna. So a vertical dipole is a pretty decent vertical antenna. It doesn't need any radials. So I was working on a vertical dipole, and I came up with a scheme where I would run a wire from the big tower to the little tower, and then another wire from the little tower to the ground. So it was sort of like a sideways inverted V. But I found that from modeling that because it was short, I didn't have enough room for a full-sized 160 meter, and because the angle of the V was narrow, the radiation impedance, the input impedance of the antenna was really crazy. It was very capacitive and it was a very low resistive component. which told me right off that if I was going to try to make that antenna into a physical reality, I was signing up for some kind of a tuner or network at the feed point. Another interesting thing here is that the input impedance that you see does not necessarily affect the gain or directivity of an antenna. So if you have for example, a beam antenna, a Yagi, maybe it's a 3-element Yagi, maybe the end of one of the driven elements fell off and the SWR is crappy. As long as you can deliver power to that driven element, and as long as the other elements are still working properly, you can still get the same gain out of it, okay? It's not like your gain is going to go down just because the SWR has changed. If you can deliver the power to that element by matching it, you'll still get the same gain out of that antenna. So more about gain. If an antenna radiates equally in all directions, that's something that we would call an isotropic radiator. And now that I've used the term, I have to be truthful and tell you that there is no such thing as an isotropic radiator. And the reason for that is because no matter what you come up with, you got to hold it up with something. And the ground is present. And so all of these factors mean that there is no such thing as an isotropic radiator. You can't actually build an antenna that radiates equally well in all directions. They would love to for cell phones and car antennas and stuff like that, but it's a theoretical concept that we use when we define gain. So in a isotropic radiator, the radiation would be equally divided in all directions. And since what we're really interested in is point-to-point communication, I mean, from here to there, from me to you, that's usually considered a point-to-point or straight-line communication. Any energy that's not going in that direction is essentially wasted. So if I'm trying to talk in this direction and I'm sending energy in that direction, that energy is wasted. So if we modify an antenna to concentrate the energy in the desired direction, that's called directivity. So directivity refers to the geometry of the situation, and gain refers to the signal strength of the situation. An antenna has a high gain if it manages to send all of the energy in the desired direction. It also has high directivity. So if an antenna radiates more in a desired direction than another direction, the increase in signal in the desired direction is called gain. And so I've already kind of gone over the demonstration of the flashlight bulb and the discussion of the squished balloon. But these are just ways of visualizing the increase in signal strength in the desired direction. And we'll see that we can also use antenna modeling to visualize that increase in signal strength. So if an antenna radiates equally in all directions, that's what's called an isotropic radiator. The radiation is, oh, wait a minute. I think it's a dupe slide. Gain compares the energy radiated in the favored direction of this antenna to some other reference antenna. And modeling will tell us what the gain of an antenna is. And the choice of the different reference antennas can lead to different units and a lot of confusion, and this is where the manufacturers will try to fool you. So if an antenna, if you're comparing its signal strength in a desired direction to the signal strength of an isotropic radiator, the units are dBi, which stands for decibels isotropic. If the antenna is compared to a dipole, which is a more realizable and real antenna, then the units are dBd, decibels dipole. And dBd makes a lot more sense for hams because if you got your license and wanted to get on HF, probably the first antenna you ever made was a dipole. And so something that hams understand very well, and it's kind of the basic building block of most antennas. Because an ideal dipole has 2.15 dB gain over an isotropic radiator, you can convert back and forth from dBi to dBd and back just by adding or subtracting the 2.15 dB. So the reason that a dipole has 2.15 dB of gain is because it doesn't radiate off the ends of the wire. It's focusing the energy, and if you looked at it in free space, the energy would be going in a pattern like a donut. So broadside to the dipole, again, I said free space, there's no ground involved. We're out there, you know, in space. The energy is going to be radiated equally well broadside to the wire in all 360 degrees around the wire. But it's not going to radiate it off the ends of the dipole. So we're focusing some of that energy in the broadside direction. Bob?
Repeat the question.
What did you say? I can't hear that again?
Yeah, unless I'm missing something, shouldn't, according to what you're saying there, shouldn't it be dBi plus 2.15 equals dBd?
Signs are backwards.
Okay, I'll accept that correction.
Repeat it.
Oh, the question was, are my signs wrong in my algebra? And the answer is yes. Probably. I'd have to stop and think about it, but the point here is that there's a 2 dB difference. And if you're reading an antenna manufacturer's advertisement, you got to pay attention to see whether it's dBi or dBd. Because this guy might say dBi and that guy might say dBd, and when you decide which one to buy, you might... What's that? Oh, we have another opinion that says the signs are correct. So,
dBi was always higher than dBd. So they're correct.
Yes,
yes.
absolutely.
Right, dBi is a lower reference by 2 dB. Okay, so we'll continue on. Gain, but wait, there's more. RF energy doesn't penetrate ground very well, and that's basically because ground is a conductor. And when the RF energy strikes the ground, as it would with any conductor, it creates a current flow. The current flow in ground, in turn, creates a new RF field. So we have RF field creating a current, creating an RF field. That's called a reflection. So basically, the RF energy is reflected from the ground. And it turns out that for a horizontally polarized antenna over ground, the reflection from the ground is going to be out of phase with the signal that's impinging on it. Now, that's not the same case for a vertical antenna. So therefore, horizontal antennas over ground have what's called ground reflection gain. And so I apologize that this picture is a little fuzzy. But essentially, if you have an antenna here, where my cursor is, everybody see that? If you look at its direct ray, it can go to this place, or it could go to this place. These are the direct rays. And you also are going to get a ground reflection. So you get a signal from the antenna that strikes the ground, creates a new current, creates a new signal, and that signal is then summed at each point in the field. So essentially, you're kind of getting the contribution from two antennas. You're getting contribution from this one directly and from its reflection. Now, its reflection from these points appears to be down here underground, but its reflection is opposite in phase. And because it's opposite in phase, can anybody tell me what you would see if you were right on the horizon? Exactly, nothing, cancellation. The two signals would cancel out. So that says you're going to get no signal right at the horizon. And that makes sense because you can't get any signal down below the horizon, underground. All of the energy has to be concentrated into the hemisphere above ground. And so therefore you're getting some gain out of that. Taking the energy that would have gone into this half of the balloon, if you will, and you're adding it to the energy from the top half. So you're getting some gain. Does anybody have any idea about how much gain you'd get?
About 3.
I heard 3. Now, are we talking watts or volts? dB, 3 dB. Okay. Charlie?
5.86.
Very good. So Charlie was gave me an exact answer that was closer to the rough answer I was looking for, which is about 6 dB. And you would get about 6 dB if you doubled the power. And that's what you get, because you take the power that would have gone in the bottom hemisphere and added it to the power that went into the top hemisphere. Now, if we consider the case of a vertical dipole, same thing happens with one important difference, and that is that the image signal is not inverted. So now these two signals are going to add in phase. Now what would you get on the horizon?
Have like double.
You'd get double. So this is why vertical antennas, like a ground plane, are good for very low angle radiation. And in certain cases that could be DX, or if for VHF it could be talking to the taxi cabs in town. So this shows that your choice of orientation immediately tells you something about your takeoff angle and what's going to happen at the horizon. So if the energy, this is just kind of rehashing what I said. Basically you're doubling the power. You don't actually get exactly double, which would be 6.02 dB. It's closer to the 5.86 number that Charlie quoted. And it's also going to be dependent on some other things. It's going to be dependent on this height that tells you at what angle they're going to add, and it's going to be dependent on the ground deflection. So typically ground is not a perfect conductor. It's got some losses. So the signal from the reflected ray isn't going to be exactly as strong as the original direct ray. So that's why we don't get exactly 6 dB, but we get close to it. So if we place our reference dipole over ground, all of a sudden it has 8 dBi of gain. So what you thought was a crappy dipole actually has 8 dBi of gain. Now, if that's your reference antenna, that means that the antenna, the unknown, the one in the shiny antenna catalog, if they're using a dipole over ground as their reference, their numbers don't look that great. They're like 7, 8 dB. But then if you look at another manufacturer and they give you numbers referenced to dBi, holy crap, they're 8 dB better, okay? So you see why there's this confusion. Antenna companies make a lot out of that, and I suspect that's why a long time ago QST stopped putting gain figures in the magazine. So anyway, that's kind of the story there. Efficiency. As I said before, efficiency is a measure of how much of the power is actually radiated in the form of electromagnetic energy as compared to the total power delivered to the antenna. So if the antenna has resistive losses, some portion of the RF power delivered to the antenna is going to be dissipated as heat. And depending on the design of the antenna, the resistive losses can be a significant part of the whole picture. And you can actually have an antenna that you may be delivering 1,500 watts to, but it's not really turning that all into 1,500 watts worth of RF. What you have is an antenna that's partly a dummy load. I've thought of, there are examples of wideband dipoles that you could buy that actually had a resistor at the feed point. That would be a low efficiency antenna. Very short verticals like the one I tried to build on 160 can be low efficiency. If the RF resistance at the feed point is only 5 ohms, then if you have an ohm of resistance in the wire somewhere, that's 20% right there. Okay, front to back and takeoff angle. So front to back is the ratio in dB of the energy going in the desired direction compared to the energy going in the opposite direction. And so this might be important if you're trying to get W3 LPL off your back, then all of a sudden you care about front to back. There are also other measures called front to side where you're comparing the desired direction to something not exactly 180 out, but maybe 120 out. Maybe they would choose front to side to correspond with a minor lobe. That's another measure of directivity. So the next thing I'm going to talk about is takeoff angle, and I'm going to go back to the example of the horizontal antenna over ground. Basically, a horizontal antenna over ground is going to have a major lobe, and the angle of that lobe is going to depend upon the height of that antenna in wavelengths over ground. And we would very much like, if we're interested in DX and contesting, to match that takeoff angle to an angle that we know is good for communication to the places we want to get to. So, for example, probably at least 30 or 40% of my contacts, maybe more, are zone 14, zone 15. So we want to try to match the vertical takeoff angles that get us to zone 14 or 15 as effectively as possible. We can get into, we can kind of go from antenna modeling into terrain modeling. And there's a whole topic that I'm not going to cover today of using what's called HFTA, which is a modeling and analysis package developed by Dean N6BV that takes into account the actual terrain at your location and gives you a figure of merit that explains how well your particular and exact antenna system matches the statistical angles for the location you're trying to get to. But I'm not going to go there today.
Question. Front to side. Front to side specifically at plus or minus 90 degrees, correct?
No, I don't think it's specifically at 90 degrees.
In my experience,
Can you repeat back the question?
Okay, the question is, Charlie asked if the front to side was specifically measured at 90 degrees. And my opinion is it's not as tightly coordinated that way. I don't think everybody necessarily uses 90 degrees. If you have an antenna that has some minor lobes off the back, then your worst case is going to be the direction of the minor lobe, and so that's probably what you would use for front to side.
right, in the software that I've used, they've offered three options: front to rear, front to back, and front to side, especially for optimization.
Mm-hmm.
And the software that I've used has specifically stated that the front to side is plus or minus 80, the front to back is minus 180. I'm sorry, front to side was plus or minus 90, front to back was exactly minus 180, and front to rear was the summation of minus 90 through the other minus.
Mm-hmm.
I think it's how the commercial antennas get spec.
So different modeling programs will give you different options to measure these things. And obviously, if you care about them, then you can pay attention to them and you can set the program up to look at whatever it is that you're particularly concerned with. So your modeling program is going to basically tell you what the front to back and the takeoff angle of an antenna is. So I'm going to talk about a couple of modeling programs here. The one that I'm going to use is called 4NEC2, and it's available at this URL. And I like it because it's free, and hams are cheap, and it's free. There's another program which is available free, which is EasyNEC version 6 demo version. It has some limitations in it, which may or may not be relevant to the particular thing you're trying to model. And then beyond that, there are a lot of other antenna programs, and I would suggest you go to this ARRL.org link to find out anything else than that. But I bought a modeling program a long time ago, something called NECWin Basic, which is also another modeling program, and that was very effective. But for the longest time, I think what happened was I probably migrated from one PC to another, and that purchased program didn't migrate well. So then I went to 4NEC2 because it was free, and 4NEC2 has worked fine. I've used it to model just tons and tons and tons of stuff. What is this NEC thing anyway? All of modeling programs seem to have NEC in the name. And well, NEC is NEC, stands for Numerical Electrical Code. The original NEC was developed at Lawrence Livermore Labs in 1981 under contract to the U.S. Navy. NEC 2, which is an older version, has been released to the public, but newer versions like NEC 3 and NEC 4 are, because of governmental security concerns, are available only as compiled binaries, and you basically need a license. And the difference is that NEC2 will work for most everything that you want, but there are some specific cases where you would want a better version like NEC4 to do some particular modeling. So I'll give an example of that. One of the antennas that I worked on quite a bit was the W6NL Moxon, which is a 2-element beam for 40 meters. It was a design that was originally developed by W6NL, and it's an amazingly good antenna. Having gone through that experience and upgraded from a 402 CD, I don't have any problems claiming it's 4 dB better than a 402 CD, which is pretty incredible when you consider you have a 2-element 40-meter antenna on a 22-foot boom here, and a 2-element 40-meter antenna on a 22-foot boom here, and this one's 4 dB better than this one. That is kind of a reality check. And in the course of doing this, the original design by Dave Leeson was a modification of the 402 CD, and it uses a lot of the, if you look it up on the web, you'll find a lot of how-tos and cookbooks, and it uses a lot of the aluminum from the 402 CD. But I decided that I wanted to scratch build it, and I wanted to build it out of brand new aluminum that I was going to buy from, I actually bought it from Cycle 24, which has now been taken over by DX Engineering. The thing is that the aluminum in the 402 CD is one certain length, but the aluminum you can buy is comes in certain lengths, which means that my taper schedule would be different. So I'd have telescoped sections, but where the joints are would be at different places. Now that can have a big effect on the resonant frequency of the element. And so I was trying to model my version of the W6NL Moxon, and I was modeling it with 4NEC2, and I found out that everything worked exactly like it said, has fantastic bandwidth, great gain, you know, very nice impedance, super great antenna. Everything I was coming out was low in frequency. So it was saying it was resonant at 6.8 megahertz. And I went back and forth and talked to K3LR, talked to W6NL, talked to K1GU, and they all said, just build an damn thing and it'll work. And I did, and it worked great. Then I put together a paper on it because it worked so good. I took it to Dayton, presented it at Dayton, and there Jordy W8, WWV, I think is his call, who's a friend of Tim, K3LR, said that he had modeled it with NEC4 and it came out right on frequency. So there's an example where NEC2 sort of worked pretty good, kind of gave me some information, but NEC4 gave me the right answer. And the difference is that that antenna has T sections where the elements are crossed. The NEC2 doesn't deal with that very well, but NEC4 can handle it. So you may find that there are situations where NEC2 isn't good enough, but I would say most of the time for initial look, it's fine. A lot of these programs are essentially user-friendly wrappers around a NEC2 core. So you'll see when I run 4NEC2, I do a bunch of stuff, define the antenna, then I run the program and it says, oh, I'm running NEC2, and then at the end it takes the data from NEC2 and shows it to me in a pretty picture. So most of these programs are essentially wrappers around the NEC2 core. So the programs try to make it easy for you to input the antenna dimensions, try to make it easy for you to visualize the results, and a lot of them will facilitate optimization. Now optimization is a process, so if you sat there and you said, I want to make a dipole for 20 meters, you might start and make it 16 feet long, and you might find that that's not resonant where you want it. Then you make it 17 feet, well, that's a little better. 17 and a half, that's good, but that's too much. 17 and a quarter. That process of iterating on a dimension to achieve a specific result is optimization. And you can get the program to do that for you. You can tell the program, I care a whole lot about gain, I care a little less about SWR, and I don't care at all about front to back. and you can hit a button and it'll go off and it'll run a whole lot of different cases for you until it finds one that meets your goals. That's what optimization is. So one thing that modeling does is it requires that your antennas be broken up into segments. And I had a question from Rich before this week about segmentation. So basically, the way that the neck core works is it figures out, it basically breaks up wires into little tiny pieces. And if you have a very short dipole, it's easy to calculate the field of that dipole if you know the current in it, because the current in that short dipole is essentially the same over the whole length of a short dipole. If you make it very short, the shorter you make it, the more similar the current is from one end to another. And that way, all the complicated math that's going on under the hood doesn't have to worry about how different the current is in that segment. So we basically break up the wires in an antenna or conductors into segments. And the goal there is to make them such that the current is essentially the same across the segment. And some programs will give you the option of auto segmentation, or you can manually control the number of segments in each wire. And the question I got was, how many is the right number? And the answer is, there ain't no good answer. It's sort of like radials. It's like, keep adding more until you see things settle down and stop changing, and then stop. You don't have to add more after that. If you have too many segments, if you have the free version of Easy Neck 6, it's going to stop working because that's the limitation of the demo version. Or if you have 4 Neck 2 and you have too many segments, it may take too long, and you may get impatient, or maybe your computer will run out of memory. So you don't want to just say, oh, I'm going to put 10,000 segments in and not worry about it. You sort of have to manage the number of segments if you don't do it automatically. And the better programs will give you a segmentation error. They'll let you know that there's something going on there that it doesn't like. Something has exceeded the error. And then that can be your feedback to go back and increase the number of segments. So that's basically the end of the slides. And now I'll go in and run 4 Neck 2. So this is 4 Neck 2. And so this is an antenna that I did at Nearfest. And I'll just start over again from scratch. So basically, I'm going to click on this icon, and it's going to let me edit the antenna file. And most programs will have you enter the information on the antenna in a spreadsheet form. Now, just to prove I'm not cheating, I'm going to say new here. So I got rid of all of that stuff. So my antenna is not there anymore. So the first thing we're going to do is define a symbol. And I'm going to say H equals 33. And that symbol is going to stand for the height of the antenna. And down here, I'm going to say that my units are feet. Now, I can have any units I want, and I can choose units that might be convenient for me. But I've done this demo once already in feet, so I know feet work. But for example, if I was doing a VHF antenna, I might want to do it in meters because I know, 2 meters is 2 meters or whatever. So I'm putting in a symbol here, and the reason I'm doing that is that by putting a symbol in at the beginning and using that symbol to define the geometry, I can then change a lot of things about the antenna just by changing the value of the symbol. So I'm going to build my dipole at 33 feet. And I'm going to define all of the dimensions of the dipole, all of the height dimensions in terms of h. And so if I want to all of a sudden say, what would it do at 50 feet? I just change h to 50, the whole thing will go up. It's easier than going along and changing a lot of things. It's not that complicated for a dipole because really I can define a dipole in terms of its 2 endpoints, so I'd only have to change 2. But if I had a 6-element beam, maybe something that had a bunch of traps in it, or a quad, you can see how all of a sudden you've got a lot of points that you have to change. So we'll go and do the geometry. I'm going to talk about it in terms of wire. Tag. So tag means I'm going to number the elements of my antenna, and tag is which element am I talking about. So I'm going to say this is tag 1. And then it wants to know segments. Now, if I want to do manual segments, or if I want to do automatic segmentation, either way I have to put a number in here. So I'm going to put in 15. And I find that 15 is a good starting point for HF antennas. I'm going to use an odd number. And the reason I'm going to use an odd number is because I have to feed this antenna with energy at one of the segments. And I want to feed it in the middle. So to get a segment in the middle, I have to have an odd number of segments. And then it's asking me the x1, y1, z1 position. And basically this is the coordinates in 3 dimensions of one end of this tag 1 wire. So if we look at the way it's going to define it, and it's giving me an error because I haven't finished that line, you can see that z is the height, and then x and y could be north and south versus east and west. It really doesn't matter what x and y are, as long as you keep them straight. All right, you go away. Go on. Okay. So I'm going to say x is 0, so we'll just have it running in the y dimension. And y is going to be minus 17 because I'm trying to make a 20-meter dipole. And z is going to be h because that's how high I want it. And then I'll do the other end. So x is still 0 because it's running north and south. Y is going to be 17. And z is going to be h. And the radius is the size of the conductor. So remember I did this in feet, so I have to know the radius of a piece of wire in feet, and I happen to remember that it comes out to be 0.008 feet. I think that's like 16 gauge wire or something. So now I've defined the geometry, and just to save myself some pain, I'm going to save the file. We'll just give it that name. There's a few more things I have to put in. I have to put in a source, and I could also put in a load. I'm not going to bother with a load for this one, so I just at least have to put a source in so that we're driving the antenna with some energy. So I'll make it a voltage source. It's going to feed wire 1, that tag 1. Now if I had a 3-element beam, I might have tag 1, tag 2, tag 3, and I'd feed the middle of tag 2, which would be the driven element. But I only have one wire, so that's the one I'm going to feed. Which segment am I going to feed? Well, remember they're numbered from 1 to 15. I want the one in the middle, so that's 8. And then I want to feed it just with a real signal, so that's simple. And if I wanted to, now you wonder what happened there, but I think, there we go, it's still there, okay. If I wanted to put like a loading coil in the antenna, then I could specify the tag number, the segment number, which would be where the coil is, and then what the impedance of the coil was or whatever. I could do all of that. Next thing I'm going to do is frequency and ground. So we're hoping that this is going to come out to be a 20-meter antenna. I'm going to do it over real ground. I could do it in free space or any of these other ground variations, which are, different things that you can look up, and I'm not going to talk about right now. You can select the ground type, and you can look up the ARRL has sources or other sources. You can find out what kind of soil you have, and that'll determine the losses of conductivity and the kind of ground reflection you got. I'm just going to say it's average soil. So we got all of this stuff done. I'm going to save the file one more time so I don't lose it. And now I'm going to go back to this window here, and now we can see my little antenna there. And I'm using the mouse to kind of walk around and change the orientation of it. This little red circle is the feed point, and it came out in the middle. That was pretty cool. Next thing I'm going to do is try to actually calculate something. So I'm going to click on the calculate button, and we're going to try to get some output data. And I think what we'll do is we'll try to do a far field pattern at 14.15 megahertz. So now you can see it. You saw that window pop up? That's when it's actually running NEC 2. And now we see the pattern. Now this is a horizontal, it's a vertical plane pattern. So the ground is going this way from minus 90 to 90. And you can see that because this antenna is roughly a half wave off of ground at its frequency, that the angle is about 60 degrees. So that's, not great. You can also see that it's like very little radiation right on the horizon. For DX, we'd really rather see the peak of this be down in the very small numbers of degrees, like around 8 degrees.
Tony, would you call that really 30 degrees? Because you're measuring
Yeah,
50 from straight.
yeah. I'd agree with that. So
What was the question again?
the question is, I said it was 60, and Bob asked, wouldn't it be 30 degrees? And yeah, it's 30 degrees off the horizon, so that would be 30 degrees. And we can also,
So the wire runs through the page.
yes,
Yes, you're looking at the end of the antenna.
yes. Charlie's question was, does the wire run through the page? And the answer is yes. So this is a dipole, and its favored directions are to our left and right here.
Does the program allow you to, let's say, put the mouse on some point of, the actual
Yep.
graph itself?
So you want to get numbers?
No, that's not what I was asking. Can you, like in some of the interactive programs on the internet, you click, let's say, on a point, and you hold your mouse down, and you can elongate or change. Do you have the ability to change the pattern, the way you see it is there, and then have it instantaneously calculate all the other things that you initially had to put in? In other words, you gave it the reference material initially, and it came up with that as a pattern. Now, can the program do the opposite, where you literally change with the mouse how it actually appears, and then have it calculate everything that you had to put in, so you know what you need to design your antenna for if you want to have certain lobes at certain wave angles?
So the question is, can you run the program backwards and go from a pattern to a hardware design? And the answer is no. And I think the reason for that is because NEC doesn't go that direction. I think NEC can only go from currents and conductors to fields and patterns. I don't think it can go in the inverse direction.
Do you know if there is any other modeling program out there?
I don't know of any that does that. So another thing we can do is we can look at the plane and the horizontal plane, and this is going more to Charlie's question. So that in this case, we're looking down on the antenna from the top, and we're looking at the radiation pattern at a certain angle. In this case, it's an angle of 62.5 degrees. And we can see the more or less nulls off the ends, and we can see the peaks off the sides. And we can see that our dipole here has 7.1 dBi of gain. Now, a thing that I really like about this program is that you can click on this button here, and it'll give you like a pretty 3D picture of the whole mess. So here's our dipole. Actually looks like a dipole, and you can see that there are these color-coded lobes that show where the strongest radiation is. So one more thing that I'll do.
Does the height above ground change the radiation pattern?
Yes, it does. The question is, does the height above ground change your radiation pattern? So let's just show how that works. So right now we see that the peak radiation is somewhere close to 62.5 degrees. We will go back in here, change the H symbol. Remember, I said this was going to be easy, so let's make it 50 feet. And now we can look at this guy, and you see that it moved up. Okay, the antenna is at a higher height. We'll calculate the far field pattern. Crunch, 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 very, very quick. And now we look at it and then we see a couple interesting things. The main lobe moved down in angle, which is good for DX, but we also developed another lobe going straight up. So that would be good for, you know, NVIS kind of stuff. So the real easy answer was yes, the height above ground does change the radiation pattern. And if we go here, we can see this. We get this kind of funny looking top hat thing. I will do one other thing, which is I'm going to take away ground and do the antenna in free space. And we'll do a new calculation. Bing, bing, bing. And now in our 3D picture, the ground is gone. It knows that. And we'll do the multicolor. Oh, and here's our donut. So this is the pattern of a dipole in free space, which is what I tried to explain with a lot of hand waving about 20 minutes ago. And we can do some other cool things. So we can calculate a frequency sweep. So in this case, what we're going to do is we're going to simulate the antenna over a range of frequencies. So let's go from 13.5 to 15 megahertz in steps of 100 kilohertz. And we'll do that. Bing, bing, bing. That was pretty quick. Don't need to see that. And now it's showing us some useful stuff like the SWR curve. So we see that the SWR is pretty decent. It's like 1.4 right around the CW end of the band. So 17 feet is a pretty good length for a 20-meter dipole 50 feet off the ground. Down here, this is the reflection coefficient, which is just another way of saying that the SWR. We can look at gain to front to back, and so it's showing the gain of the dipole, 2.14 dB, that's right. Front to back is 0 because it's the same in the 180-degree direction. It has no front to back. We can look at all kinds of other things like what's the impedance and phase of it. So the impedance is 72 ohms, and the resonant point is right about there. So we can see all kinds of interesting stuff about the antenna. We would know if we were going to build this antenna, I could feed it with 50 ohm and have a 1.5 to 1 SWR, or I could feed it with 72 ohm and have a perfect match on the feed line, and then have to deal with that in the shack. So hopefully I've shown you enough that you could go and download 4NEC2 and follow the steps that I did and put in a dipole and simulate a dipole and see what it's going to do. Dennis?
Yes. Is there any place where you can download fixed antennas, say a 104 CD?
So the question is, can you download antennas that are already done? And the answer is, this one comes with a whole lot of stuff. So basically, it installs the file called models, and then you can look in the various subdirectories. So you see there's a lot of stuff here. So there's like HF beams. I can open up my file for the 402 CD Moxon. And actually, this is a good example of something that I'll show you in a minute. But to answer your question, you can get files that come with it, but I don't think there's any central location where you can get files for just anything you want. Some manufacturers will give you files. Some antennas are impossible to model. So like the KT36XA, good luck with that one. Yeah, I would definitely say you're going to need NEC 4 for that one, or maybe NEC 18. Charlie?
I have a library of antenna models in several formats, so there may be other members that do. I would suggest if you're looking for something specific, regardless of the format, post an email to the collector about what you're looking for, and eventually get some answers.
Yep, that's good. Charlie says that he's got a lot of models, and that a good way to get models is to ask around. You can ask on the reflector. You can also ask on CQ contest or Tower Talk. You know, people exchange files there. Rich?
Tony, I'd like to ask the group the question that you and I talked about, whether there's any graphical interface that allows you to get around the spreadsheet and put the data. Anybody aware of anything like that? Where you could actually, with a mouse, manipulate the model to go forward instead of backwards. You know?
What?
I worked on some software a couple of years back, which would allow you to basically model it like a Yankee in the CAD software, and then do basically what then convert back to a spreadsheet. But it proved quite challenging. So I have something that sort of does that, but I don't know of any published software that.
All right, let me just hit one more thing here. This is the Moxon antenna. I'm going to change the segmentation on it. And I'm going to deliberately put in too few segments. So auto segmentation basically means that the program goes in and does the breaking up of elements. And I just reduced the number it's going to use from 60 to 10. And now I'm going to tell it to do a calculation. And it comes up and says errors or warnings found, run segment check. So then you see here it's highlighted some areas into the antenna in red, and that's telling me that I don't have enough segments. And so if I go back, I have to turn it off and then I have to turn it on again, and I can say use 60 segments, which is quite a lot compared to the 15 I was using in the dipole. Now I can go back and tell it to calculate again, and it works fine. Bob?
Are you able to, right now, demonstrate the terrain modeling aspect of this? Like how you would put data in and then what it actually does, how it uses it?
So this program doesn't do the terrain modeling. The terrain modeling is done with a program called HFTA. And to explain that, it would be an equally long talk. But essentially the way it works is you can obtain a topographical map of your area, and you can either do it by hand the hard way, or you can download data from some sources that'll give you what the geography of your area is. You specify what antennas you have and at what heights, and it will calculate the takeoff angle. It'll give you an exact vertical profile, and then you also specify where you're trying to talk to. It's like you'll say, I'm in Connecticut and I want to talk to England. And it'll pull up specific files that tell the program what the favored angles are and the statistics of those angles.
Specifying each way that way.
Yes.
No, you had mentioned something about terrain modeling, so I thought built into this program, it would actually model your terrain with the antenna that you designed over there.
I'm sorry if I implied that it was in this program. It's not in this program.
So essentially it's doing it for all intents and purposes until you have perfectly flat ground.
Yes. Yes.
Or free space.
Or free space, or, you know, it could be good ground, bad ground, whatever you want.
Follow-up question, you mentioned there are certain antennas that are going to be very difficult to create a model. So KT34 or XA, for instance, XA, they come up on these very often. If you were looking at a problem where you were interested in interactions between antennas, in that example, let's say you were stacking 34s, not that I'm going to do this in the near future, but if you were trying to figure out interactions, do you believe that you could do that just by putting an equivalent Yankee, say a 3 or a 4 element, and then putting the other antennas that you were concerned about interactions with? Would that be adequate, or do you need full detail?
So there can be interactions between active elements of antennas, and there can be interactions between active elements of one antenna and a structural element of another. So the best example I can give is the 2-element 40 underneath a KT36XA. And the boom of a 36XA is resonant in 40 meters. And so I had the two about 9 feet apart, and I could definitely see SWR going all over the place, which means I'm guaranteed to have an interaction. I was able to model that, but I was essentially modeling the XA in a very simplistic form. I wasn't modeling its traps. I was modeling it more as 20 meter elements. And I was able to see the interaction. I think when you start,
If I was to take a structure like a, KT-34 like structure with 4 elements, artificially create the resonance at the frequency I want it. Like, for example, loading the element or something like that. That might be a way of creating something that is sufficiently close for interaction.
yes, yes. But you'd have to be aware of the fact that you were making an approximation. Charlie?
So a short comment about that, most of these, the program you're demonstrating and some other programs are designed to really handle either one antenna with one feed point, whether it's a multi-element Yankee or dipole, as opposed to a complex array of elements that can be interactive with each other.
So,
I think from a user standpoint, you want to first get comfortable using this to make a dipole, make 2 dipoles, make phase dipoles, make a Yankee. Then you want to move into those more complex antennas like interactions and other things. If you're new to modeling, expect to waste dozens, hundreds, whatever you want to, hours of time playing with this stuff. And W1TR has handled quite a lot.
I wanted to ask, does this deal with feed lines?
yes, you can include feed lines as much as they are a part of the antenna. So if you're using a piece of feed line as a loading stub,
Let's say 100 feet of ladder line, you can model that connected to the antenna.
well,
See what its impedance is.
it doesn't really handle that. So the way to handle that is to use this program and find out what the impedance is at the feed point, and then use something like TLW and put that in. So, go ahead.
For $100 or $200, can't you get a capable version of EasyNac? And is that worth doing as opposed to this free version?
So the question is, can you get a capable version of EasyNet for dollars? And I'm sure the answer is yes. Is it better than this one? I'm somewhat skeptical. Even with the known limitations of the Moxon situation, I didn't feel the need to spend dollars. I felt I was getting reasonable information out of the free version. Brian?
Tony, having used both of those programs actually frequently, side by side, I would say that in my opinion, my experience, it's easier to enter antenna descriptions into EasyNet than it is to enter them into 4NEC2. I'm more comfortable with the editor in EasyNet. They're both running the NEC2 engine, so they're going to give you identical results. 4NEC2, because it has additional features, tends to be somewhat more complex, I think, to learn how to use. And one thing that I think is important is the angle conventions are completely different in 4NEC2 and EasyNet. Someone asked, isn't that 60 degrees that Tony described really 30 degrees? That's the angle convention in 4NEC2 versus the angle convention in EasyNet, which is much more like what we hams are used to using. And the other, somebody was asking about a repository of antenna models. Is there a reflector, Tony, for 4NEC2, a discussion group?
I don't know of one. There might be.
Okay, I think there is one on Yahoo, which of course is a problem, but that's another place to go if you want to look for this.
So one point I'd like to make is, in terms of models, this program can read models from other programs. So there is some degree of interoperability. So if you get a model from somebody, but it's for EasyNet, then this can read it. All right, one more question, John.
How much processing power does your computer need to do what you did?
I would say not too much, and it's most likely just going to be translating time, so I wouldn't think that this laptop is really the spiffiest laptop, and it seems to be able to handle these cases pretty easily. But I don't think that's an issue anymore.
I'd say the ARRL antenna modeling book, it's actually pretty
Yeah, and it comes with a CD that's full of stuff.
Has HFTA.
Those published designs are pretty good.
Yeah, that was pretty good.
So I think I'm going to cut off the questions at this point in the interest of getting through the meeting.